Okay, welcome everyone. It's a great pleasure to have Chen from Peking University as our speaker today. Yuan is a young assistant professor at Peking University, and he has already done a lot of interesting work on topological physics, lattice gauge theories, generalized symmetries, and error correction codes. When I first met Yuan, I already knew that Yuan would become a superstar. It's not only because of his achievements and potential at that time, but more importantly, because of his passion about the physics. In particular, the purity of his passion about physics. I'm sure we can also see some of that aspect during this talk. Yuan, please go ahead.
Yeah, thank you very much for the nice introduction and the invitation to give this online talk. So in today's talk, I will focus on my three paper list below. So I have done lots of work with my student. So the first three are my student at Peking University. The first one, Han Yu, he already moved to MIT as a PhD student. And for the second one, Yi Tao, he is probably going to MIT as well. So he is a senior. Yeah. So they are the main driven force for those projects. And I need to also thank my collaborator Liu Hei, Paul Shen, and Meng. Yeah. So they also help me a lot on these three papers. Yeah. Okay, before I go to any technical uh, details, let me just give you the motivation of my talk today. So it's called generalized statistics. So basically, in quantum mechanics, we learn the statistics as bosonic, fermionic, and also anyonic in 2D. Yeah. So I will try to generalize the notion of these statistics into higher dimension. Yeah. So since maybe the first course in quantum mechanics, we know when we exchange the particle, we can get a plus minus sign. So for general dimension, and in particular in 2D, there's a more exotic behavior. It's called anyon statistics. So which means when we exchange the particle, the phase can be any U1 phase beyond the plus minus one. So let me explain introduction why those dimension, the behavior in different dimensions are so different. So first, we need to notice a property. When we exchange the particle twice, it gives you the full braiding. So now consider A1, A2 are identical particle. They can be electron or any fundamental particle. When we do this exchange twice, so topologically, so this is the wall line of my particle. So the horizontal direction is my spatial direction. You can think it's like a 2D spatial. I didn't draw the additional direction. And the vertical one is the time direction. So as times go on, it exchanges twice. And this wall line is topologically equivalent to this one. So here I just try to make this A1 wall line become straight. And this A2, it go behind this line and go above this line. So this is the space-time diagram. So on the spatial manifold, it's nothing but this A2 go to behind this A1 and coming back. So this is the full braiding of these two particles. And the full braiding in 3D or higher is trivial. The reason is the following. So consider my original wall line is something like this. But in 3D, we can leave this wall line into additional dimension. And so it becomes outside the plane. And then we can shrink this wall line a little by a little and to a contract to a point. So which means this braiding is completely trivial in 3D. So which means the theta here can only be plus minus one at most. So that's the reason why the anyon only appear in 2D, but in 3D and higher, we only have boson and or fermion. Yeah. Okay, so this is a very simple picture, and it's well known for every one who studied quantum mechanics or condensed matter before. So there are some natural questions to ask. So first, we discussed the particle in 2D and 3D and higher. So how about a particle in 1D? Yeah, so this is, so let people talk about this. Now there are some subtlety we will discuss. And also, how about the loop excitation? Because we know in 3D, like a superconductor, there are some flux loop excitation. So can we discuss the statistics of loop in 2D, 3D, or higher dimension in any sense? And also, because for particle, we have fermion, sorry, we have anion. So for loop, is there any anionic loop excitation? And a similar question can ask for membrane excitation. Yeah, so in this talk, I will try to answer those questions for you. And for now, I will just provide you a short answer. Yeah. So the particle in 1D, they have some fusion property. It's usually called F symbol in fusion category. Yeah. So in literature, people do not think of this as a statistics, but in my notion defined later, I will try to unify. So that this fusion process is very similar to the exchange of braiding statistics in higher dimension. Yeah. So how about loop excitation? The loop in 2D, it can fuse. In high dimension, the loop can flip. Like given a loop, we can flip this loop by pi, and we can ask whether this flipping give you a plus minus sign. So this is called a loop flipping Z2 statistics. Yeah. And there's no anionic loop excitation. So remarkably, in one of Chen's paper, he showed that in the 4D torical, so typically in a torical, we have E charge excitation and N flux excitation. And in the 2D case, when we composite these two types of excitation to forming the EM type excitation, in 2D, EM particle is fermion. But however, in 4D torical, EM loop is still bosonic loop. So there's no anionic loop in any dimension. Yeah. And let's move on to membrane. So for membrane excitation, it becomes more exotic. So there are something Z2 index, just like the particle and loop, we have some Z2 statistics. So this is true for membrane. And beyond that, there's additional Z3 statistics. So in other words, in any arbitrary dimension, the membrane statistic at least has Z2 times Z3 index. Yeah, I will, this is highly non-trivial, and I will explain the reason, and I will define some unitary process on lattice to tell you how do we detect this Z3 index. And is there anionic membrane excitation? The answer is yes. And they also behave quite differently because it has anionic membrane in these three different dimensions, d equal to 4, 5, 6, and the statistics becomes z2 times z3 for d greater than 7. Yeah, so this is also quite non-trivial and special, and I will explain the reason. Okay, so now let me give you the outline of the physics consequence of this generalized statistics. Yeah. So first, a lot of condensed matter system like the topological phase, topological order, spin liquid, they depends on the property of the statistics of this excitation of quasi-particle. Yeah, the first example of course is the anion, like the fractional quantum Hall effect and torical. Yeah, so they are already known for maybe 20 to 30 years. And also, the non-trivial statistics will imply some non-trivial behavior for the low energy spectrum. For example, if we have boson, we can condense, and for fermion, we cannot. So this statistic will govern some low energy behavior for our system. And for the third point, you can think of this as the slogan of my talk or our paper. So I will try to define the 't Hooft anomaly of certain symmetry by the generalized of the statistics of the excitation in a symmetric subspace. So I will make it more precise. The basic idea is given any symmetry, we can study the commutant algebra of this symmetry. So which means we need to find all operator that commute with the symmetry. And this operator corresponds to a certain excitation in my system. And I will show that once it has 't Hooft anomaly, the statistics of this excitation in the symmetric subspace will have non-trivial statistic index. Yeah, I will show you some simple example later, but you can think of it just kind of the some main point or like a key point of our result. We try to define the latest version of the full anomaly. Yeah. And so this is related. So we know that the full anomaly is classified by SPT. So we will show that our latest definition match the classification of SPT in one higher dimension. Yeah. And also, once we have the non-trivial statistics, it will have some dimensional consequence. So for example, if we have some non-trivial statistics, it will require the eigenstate to be long-range entangled. So there's a recent paper by Benny Yoshida. He say if the system has fermion or anyon, the ground state cannot be short-range entangled. So we just extend their result into our general case. So any non-trivial general statistics require long-range entanglement. Okay, so let me start with the simplest case. So we first discuss the particle exchange in 2D. So, but in lattice, we need to be careful. We cannot arbitrarily just change the position of 1 and 2. So consider we have a particle at 1 and 2 here, and we want to exchange them. We need to follow a very specific process to make sure under this process, there's no additional Berry phase or geometrical phase arise. So this is the following process. Consider a junction of like this. So in a triangle, there's a center point here. So this is called a T-junction. So this T-junction is invented by Michael Levin and Xiaogang Wen back to maybe early 2000. So we have two particles here. So these two particles, they are identical particles. I use different color just for indicating for the like to keep track of which one go to where. Yeah. So at beginning, left is red, right is blue. So I move this red particle into middle, like here, and go to top. And then I move the blue particle from right side to the middle and to the left. And finally, I move the red particle down and go to the right. So compare the initial and final configuration. We can see the position of this red and blue particle, they change. So this T-junction process exchange the position. And more importantly, this is designed in a nice way. This process doesn't depend on the particular choice of this string hopping operator. For example, if somehow I redefine my U01, the hopping between the position 0 and 1 with additional phase phi, and accordingly, this U01 minus will have the phi minus here. Yeah, so which means no matter how we choose our hopping operator, or even I can redefine the position of 1. So I can move this 1 slightly to the left or choose a larger lattice. So we will show that this is the topological invariant, which is robust against any local perturbation. Yeah. So this is designed by Michael Levin and Xiaogang. So they say in any lattice system, we can use this process to detect the topological spin of any. So let me make it more precise. So consider we have some configuration state A. So for example, this A is a particle with on the vertex 1 and 2. And we apply some string operator, US. So S here can be like a 0, 1. It will create a particle at 0 and 1. So when we apply the string operator on some configuration state, it will change the configuration. So in this case, it's very simple. It's just the original configuration plus the endpoint of string, because the string operator will create two particles at its endpoint. And this phase is arbitrary because we can define the state to the other state with the different phase. So this theta here is not physical. It depends on our convention or choice. So you can think of this theta is something like a gauge dependent quantity. So the gauge means we can choose a different lattice or different state. Yeah. But given this
Yeah,
setup,
yeah,
any question? Yeah, right.
yeah. A here, remind me, A here means a configuration of what?
Of particle. In this case, it's particle. So here A is the Z2 field living on each vertex. For example, this is particle here and here. We label this by 1, and there's no particle here. We label by 0. So this A is the Z2 cochain. You can think of like this way. Yeah.
But then in this way, you are already assuming it can be described by some kind of Z2 code chain.
Yes. So yeah. So A is not physical degree of freedom. So A is the position of your excitation. Yeah.
So
Yeah,
what does partial S represent?
It's the boundary. So which means given the string, the partial means the endpoint of string. Yeah.
so in a generic system where, for example, the particles have some finite extents, the
Mm.
position requires some definition, right?
Yeah. This is a very good point. The lattice shown here is not a microscopic lattice. It is something after cosine. So you can think of given some microscopic lattice, I can define a huge lattice. So this is called 0, this is called 1. And I can define something around the 0 as my particle excitation and something around 1 as my another particle excitation. Yeah.
Okay.
So
And
that's
also here, I suppose this U doesn't really have to be unitary, does it?
in my case it is unitary, but I think for non-abelian or even non-invertible symmetry, it can be generalized. But for my purpose today, everything is unitary because I want to take the inverse.
Uh, but I think the crucial equation is just the one you wrote in the above, which says this U operator acting on the A state gives A plus partial S with a phase. This equation doesn't require to be unitary.
But I want to apply it back. Yeah, I think if we require it's invertible, like I think it will somehow imply it's unitary. Uh,
I'm saying what I'm trying to say is I think your formalism can actually be further generalized without assuming that U is unitary.
yeah, that's a good point. Maybe we can discuss this later. Yeah, I think
Mhm.
because I want to generalize our setting into non-Abelian in NL two. Yeah, but
Uh,
here
uh,
we assume
Sorry,
everything is invertible.
just to clarify, what I mean is even for abelian anyons where the one form symmetries are all invertible, I don't think we have to assume U here to be unitary in order for the entire formalism to work.
Mm.
If it's
Yeah,
unitary, then it works. Even if it's not unitary, I think it still works.
yeah, but here you in our case it obtains from the truncation of the one form symmetry. Yeah, so one form symmetry is applied on a closed loop, and I choose a particularly truncation, and I assume everything is a finite depth circuit. So here U is just a product of some local gates. So this is a very important property I will use later. So
Uh-huh.
this yeah U is finite depth. So its commutator will have some locality constraint. Yeah, I will mention this later. Yeah.
Mhm.
This is a key assumption. Yeah.
Just to comment on this, there was a later paper earlier than your paper, but later than this Levin Wing paper. In 2019, there's a paper by Kawago and Michael Levin.
Hmm.
There they could do similar things, and they didn't have to
Yeah.
assume that these operators are unitary.
You are saying this paper,
Yes,
right?
yeah,
Mm,
no assumption of unitarity is needed.
yeah. That's a good question. I will double check later. But I think in our setting we focus on a simpler one. I'm not sure whether my assumption will break down or not. Yeah. I will go through the detail once I use the finite depth circuit. Yeah.
Mhm. Thanks. So
Right.
just to clarify, what I mean, suppose you are talking about abelian phases. I think you can
Mm-hmm.
choose U to be unitary, but you don't have
Mm-hmm.
to do so.
I see.
Mhm.
Okay, so yeah, so assuming we just obtain some U1 phase when we apply the string operator onto some convolution. So the U1 self, yeah, the single U1 phase alone is not physical, but we can find some combination like the Berry phase of certain process. So certain combination of them is physical. So you can say this become gauge invariant. So we can check if we redefine the unitary by any phase, if we add any perturbation nearby the end of unitary, or we choose a different initial excited conversion, those quantity they are invariant. Yeah, so this is called a topological spin of NM. So our goal is kind of simple. For general case, we are looking for certain linear combination of this phase factor, such this combination is meaningful, has some physical interpretation. Okay, so next, so far we have said this is some robust invariant, and next we need to show its quantized. So for example, given a Z2 particle, the spin must be quantized into certain value. So how do we see from the lattice? This is a quantized invariance. The strategy is the following. So there are some locality identity need to be satisfied for this unitary operator. So let me give you an example here. Consider these three edges, 0, 3, 0, 2, and 1, 2. If they have no common overlap, so which means the intersection of these three edges vanishing, the triple commutator, maybe I should call it double commutator. Anyway, so the commutator here must be identity. The reason is the following. So assuming this U is the finite depth quantum circuit, when we compute the commutator, the support of this commutator will be live around the intersection of 0, 2 and 0, 3. So in other words, when we compute the commutator of 0, 0, 2 and 0, 3, it becomes some point operator around the center point 0. So this is what the first commutator does. And next, if I try to compute the commutator of this point operator and this 1, 2 string operator, because they are spatially far away, the commutator is identity. Yeah. So there are many identity, those theta they need to satisfy. So for example, this double commutator will give you a unitary operator. So this A unitary operator will give you this A different phase factor. So they need to sum to 0. Yeah. Okay, so this is one locality identity. And we can show that once we apply my T-junction 4 times, so this 4 times loss theta can be decomposed into the product of this locality identity. So which means 4 times this T-junction must be equal to 1. So this T-junction process can at most give you Z4 statistics. Yeah, so this is the key. So because this unitary operator have some locality constraint, so this will impose some condition on those theta. So those theta is not independent. And we can show that once we apply the T-junction 4 times, this becomes a trivial combination, and this must be equal to 1. And this give you the quantized invariant. So in my above derivation, I use the Z2 fusion rule. So which means there's only particle or no particle. But for Zn particle, you can show that the statistic will in general become Z2n if n is even, and if n is odd, it's Zn. Yeah. So I think this is a very clean way to show why the spin must be quantized on the lattice level.
Yuan, here
Yes.
commutator is defined as it's not the
Uh,
difference, it's
it
the
is the group commutator, like the A minus B minus A B. Yeah.
A inverse B inverse AB.
Yeah.
Mhm,
It's a
thanks.
product group, like for the product of group. So this is a commutator in the group. Yeah. Yeah, that's a good point. Yeah, I should write it here. My bad. Okay, so now I think we have understand what's going on in 2D T-junction very well. Yeah. Okay, so now let's go back
So
to
Yuan, I have one more question. Uh, what's the significance of having a gap here?
mm, we don't require a gap. So the only assumption is this U to be finite depth circuit. So if it's gap and invertible, it's easy to show this is the finite depth circuit because you can say you can create a particle antiparticle, particle antiparticle, many pair of them, and you can repair them. So you can have only finite depth and moving the one particle from here to infinity. Yeah. So if it's gap, I think it's let me see. I think I don't require a gap at all. As long as the excitation is invertible and this U is finite depth circuit, my argument can work. Yeah.
Uh-huh. But perhaps there's an example I constructed with some other paper in a paper with some other people where
Mm,
we considered some lattice version of R one-form symmetry. It's
yes,
a
I know.
horribly gapless system. And one can also define the T-junction and see that the statistical phase factor coming out from that can be any U1 phase factor. It doesn't even have to be some root of one unity. It doesn't have to be root of
Oh,
unity. But
mm,
then what happens there is because that system is so horribly gapless, those so-called anyons are not really anyons in the sense
mm,
they are not stable at all.
mm.
So I think in a lattice, this stability ultimately requires some kind of assumption that we don't fully understand. We don't fully understand rigorously at the moment.
Yeah,
Can I
in
make
my
a comment?
setting, I need to assume the excitation is discrete. So I can
Oh,
count a
can I
particle
make a
like a
comment?
0, 1, 2. Yeah.
Can I make a
Sorry,
comment?
yeah, Liu Hei, go ahead.
Well, in order to establish this quantization, it's important to assume the finite group, right? This one symmetric group must be finite in order to establish the quantization.
Yeah,
Yes.
yeah.
Yeah, yeah. So in the
But
case of
I
the
think
R one symmetry, I'm not quite sure how it looks like.
I I even if it's discrete, I think the property of Hamiltonian may still play a role. For
Do you
example,
have some example in mind? Well, this argument doesn't quite well assume the gapped
for
nature at all.
example,
Just
yeah,
that
yeah,
the symmetry operator is
I
yeah, a
understand
finite
this
circuit.
argument is fully
Yeah,
about the symmetry
exactly.
properties, but the question is whether these symmetry properties should be interpreted as some properties of anyons. I think that requires some properties of the spectrum of the Hamiltonian. A particular example is just to consider Toy code with the modification. So in the standard Toy code, the mm, there are
Well, I
two
would say, well,
terms.
once you have a finite circuit, symmetry just generates a finite circuit, one can take some truncations, and independent of the choice of truncations, as long as we have some nice property about the symmetry defects so that it fuses into the group, aligned with the group algebra, then one can establish such a invariant. So as long as your a defect satisfies some suitable group algebra, then one can establish such invariant without assuming gap natures. Right?
You can establish this invariant, but the question is whether this invariant of course is mathematically well defined. The question is whether it's physically significant.
Well,
I
I
think
would say
here
it's important because it's anomaly. It's a truth anomaly of the symmetry.
no, I don't think so. You can
Yeah,
define it to be the Hooft anomaly, but whether it's for example, here you didn't really justify under perturbations to the Hamiltonian what you call anyons are stable.
Well, like one consequence of this invariant is that there exists no like a state which preserves this symmetry. Well, short-range entangled state which preserves this symmetry. So maybe capless states is compatible with this
The,
symmetry. Well,
the,
this is the signature of the fifth anomaly, this invariant.
the stability of one-form symmetry is true intuitively, but it has never been understood in lattice systems.
Well, I'm not sure what we mean by stability, but yeah, okay.
So
Yeah, but
I'm just saying, suppose you just have this kind of symmetry, I don't think you can conclude there's any anion at all. For example,
yeah,
I can
I
take
think
the Hamiltonian to be zero. You also have all the symmetries of the toy code, but you don't say there are any anions.
Yeah, let me try to clarify. So here, I think I don't have a notion of Hamiltonian there. I only have the notion of maybe higher form symmetry, and I need to choose a way to truncate the symmetry. So for example, truncate the closed loop to be in the open string operator, and it will create some defect at the endpoint. So maybe this defect has some energy in your torical Hamiltonian, but here we just don't care. We are interested in the operator itself. So what kind of algebra it obey? So this open string operator don't commute. So once we compute certain quantity, let's give you some non-trivial index. So this index will characterize whether the symmetry has 't Hooft anomaly or not. Yeah, so I think this is also the point of Liu He. Yeah. So here
Yeah.
we don't talk
Mhm.
about any particular system. It's more like the dynamic, like a kinematic one that we have some general symmetry. We want to understand what's going on.
Yeah, I
Maybe
fully
maybe the
understand this.
story.
Yeah, I fully understand this and I fully agree with you.
Yeah.
My comment is on whether this mathematically well-defined invariant has any physical significance in terms of the statistics of the particle.
Mhm.
I think that depends on the Hamiltonian. It's not just the property of
Right.
the
Yes.
symmetry.
I will give you a very concrete example on the boundary of SPT. It will move some domain wall, and this domain wall excitation will have some non-trivial statistics. Yeah.
Yeah, I understand there are many, many Hamiltonians in which this entire consideration does correspond to the statistics of some particles. But there are
Yeah.
also other Hamiltonians where it doesn't. For example, I can take the Hamiltonian to be zero, and you can
Mm-hmm.
define all kinds of one-form symmetries, but you cannot conclude there are any anions.
Yeah, I agree. Yeah. Yeah,
That
but
is not our
but
claim, right? Like we are not saying that any, well, like this must be always understood as anions or like
yeah, so it's
yeah,
more
we're not
like
making
we are
that claim.
given. So our excitation model is given. So we assuming some system maybe they already have some this anion picture, and we can interpret our quantity as some statistic of this excitation. But I think we can just study this as a pure math problem. So we forget about the physical consequence. This is a very well-defined question, and it already has some interesting pattern. Yeah.
Yeah,
So
yeah,
this is
yeah.
why I'm going to
Yeah,
present.
I fully agree with this. But I think in the future it may be good to further understand under what physical conditions the mathematical environments constructed here really correspond to the statistics of some particle excitations.
Uh, yeah, yeah, I will come to later. So maybe let me continue, and later maybe you are we have time. We can continue discussion. Yeah.
Sure, sure.
Yeah. Okay, so now we just finished the story of 2D anion change, the T-junction process. And now let me step back into 1D. So actually in 1D, T-junction of course doesn't work because we don't have the additional dimension to design this trijunction. So only thing we can do is do the fusion. So the vertical is the time direction. So we can consider we have three particles A, B, C. If I fuse A and B first and then fuse with C, we can compare this process with B and B fuse first and then fuse with A. So for abelian anion, this fusion is one dimension. There's a single outcome of this anion. So I don't have any label here. So these two fusion process has the relative phase called F symbol, like FABC here. So this is the general picture for when you learn like a fusion category theory. And on the lattice, there's a recent paper by Kyle and Michael Levin. They try to put this onto the lattice. So you need to obey a very specific rule to fuse those particles. So the single rule is like the fusion can only happen in this position 1. So they need to keep track of this fusion, and then you can compare these two different phases. So this is the latest version how we compute F symbol. So we need to compare these two processes, and the relative phase is F symbol. However, the single F symbol is not physical because we can always redefine my state to make some gauge choice for this gauge transformation for this F. So there's a quantity, it's a product of F. This is the invariant. So if you are familiar with the SPT, this is nothing but you compute the partition function on the length space. Yeah. So this will give you some Z3 is a partition function computing on the 3-dimensional space-time manifold. So this is the invariant we can compute. So you can plug in into Kyle's construction. So this F involves 10 unitary operator. So this 2F will have 20 unitary operator. It's very long. I don't write it out, but you can believe in me or check their paper. And we find that we can further use some locality identity to simplify this 20 unitary into this single 2 unitary here. Oh, sorry. So this becomes a commutator of the U01 square and U12. So let me explain this U01. So this U01 is the hopping operator of the particle moving from 0 to 1. And U12 is moving from 1 to 2. So this expression is first discovered by Caroline. So in her the single author paper, the SPT entangler, he showed that in the 1D SPT, the boundary of the 2D SPT, so in the 1D boundary, you can use this unitary operator to detect the non-trivial SPT. So in our work, we just unify those two quantity. Yeah. And you can see once we reach this final expression, the geometrical meaning of this F symbol become highly non-trivial. Like it's almost impossible to go from this expression to go back to this. Yeah, so this is kind of the drawback of our approach. We can only give you the final answer, but what does it mean geometrically? Like how do I see this correspond to fusion? It becomes very unclear. Yeah. Okay, so and we can see in 1D, the Z2 with Z2 fusion group, the non-trivial F symbol is FSSS equal to -1. And this corresponds to the semion. So in other words, the boson and fermion, they have a trivial statistic in 1D. So we cannot distinguish boson and fermion. Only the semion can be detected by these statistics. So there's a reason why in 1D, we can condense fermion. So there's a notion of the higher gauging in Su Hen's paper. So he said in 1D, we can actually condense fermion and get some defect. Yeah. So I think let's explain, because in 1D, we don't have any statistic invariant to detect fermion. So we can just treat the fermion the same as a boson. Okay, now, so far, I just review the people already know in literature. Yeah, so although this 1D example may not be that famous, but I think more or less people in this field know this already. And now let's move on to something more exotic. So we now try to consider the loop excitation in higher dimension and what kind of statistics it can have. So the setting is very similar. We consider the tetrahedron 1, 2, 3, 4 with the center point 0. And so this is my physical space. And on each line, it can support the loop excitation or not. The only requirement for us is we require the loop to be the closed loop. And the closed loop is created by the membrane operator on any phase. If I apply the membrane operator on any phase, it creates a loop on its boundary, like a partial IJK. Yeah. So this is the following process we find in our paper. So we start with a certain configuration and we apply some unitary operator. For example, this is U023, which means I annihilate the loop around this small triangle. So this will change the shape of this conversion into this one. And similarly, I apply the 012. The 012 is this little triangle. So I annihilate the loop on these three edges. So these two edges disappear and become this one. So I can apply my unitary operator to move the conversion of my loop. Yeah, so I need to emphasize my loop is Z2, and the orientation here doesn't have physical meaning, just for you to compare the initial and final one. And you can see once I go through this 24-step process, for example, in this last conversion, I apply 012, so I try to attach the loop on this little triangle. This go back to the original configuration. And the only difference is the orientation is reversed. So after we go through this process, we reverse the loop orientation. And we claim if we obtain a -1, we call it fermionic loop. So this is the latest definition. You can think of it as the naive generalization for this T-junction process. Just in 3D, we need to make sure everything cancel out locally. So this requires very, very long steps.
Excuse me.
Yes.
So I have a question, maybe a basic one. So why are we interested in the statistics of the loop in this form? I mean, is there any fundamental reason, as fundamental as the statistics of point-like particles?
For point-like particle, like the fractional quantum Hall, those kind of system, they have anion. So study the anion can help us to understand what's going on. And for loop excitation, in some particular case, like O fermion QED3 or something. So in some exotic system, we do have the anomalous loop excitation. So we want to give it some index. Yeah. So here you can think of it's purely mathematical question, but they do appear in some system. So for example, in the 4+1D T-gravity, so this is my previous paper with Paulson, we construct this W2, W3 invertible phase, and we show that on the boundary, they do have this fermionic loop statistics. And there's another perspective by C.O. Johnson-Free. So he tried to study the fusion 2 category, and he proposed the invariant, which is exactly this one. He called it Klein-Bartle invariant. So he used this to distinguish different Brady fusion 2 category. So you can think of this as like a mathematical tool. We can compute certain index. And this index can help us to differentiate different theory. So we want to say that theory A is different from theory B. We must have some quantity to compute to show that they are different. So previously, the T-junction process, the anion statistics, is one possible way to distinguish different theory. We say, okay, this fractional quantum Hall state is different from the other because of the anion fusion rule or anion statistics, they are different. So here we just try to provide more tool, although it's very abstract because it goes to very high dimension like a 4D, but mathematically it's a well-defined problem. Yeah.
Thank you very much.
Yeah. So this is a
Yeah.
very long. Yeah, go ahead.
Yeah, so for this process, do you have a similar cartoon picture as the reading of particles? Like, say in 3 space, I draw a loop, I draw 2 loops. What am I doing with it?
Sorry, so here we don't have particle excitation. So we can say we just have some loop excitation, and loop can move around the space.
Yeah, I'm asking so in 2D you have the cartoon picture of the breeding of particles. We just have two particles and one moves around the other. Here, suppose I draw two loops. What is
Also
this?
here there's only single loop, and this single
Oh,
loop is just flip. Like if I can you see my hand?
yeah,
So
I
consider
can.
the loop like this. I flip it like this. Yeah,
I see.
yeah.
Mhm.
Because the loop is S1 and the particle is S0, the zero sphere. The zero sphere has two vertex. So that's why you think we need two particle. But you can think of this two particle is the zero sphere. And the loop is one sphere.
I see.
Okay? Yeah.
Thanks.
The, yeah. The study of this has long history. So it's first proposed by Ryan. So it's more than 10 years ago. He has a very few theoretical argument that we have some W3, the third Stephen Winning class, W3 abstraction. So this can help us to define some invariant. And the seal, he also gives some fusion two category description for this invariant in some very also abstract way. And I think the first one proposed this process is not me. It's by Vygotsky, Ha, and Hastings. So they have this loop fitting process, but they have a 36 step. So it's slightly longer, but they are doing the same thing. So they try to flip the loop and make sure everything local cancel. Yeah, so this is a very important criteria. We need to make sure that everything happen locally, they cancel out. So once we redefine the unitary operator or redefine the state, this process is invariant. Yeah, so this process is first solved by Vygotsky. They have some very heavy computational way to find this process. And now I try to derive this by hand for you in this talk. Yeah.
Yuan, can you hear me?
Yeah. Yes.
So for this to work, I think one thing you said you require is that you have a Z2 loop. So loop
Yes.
flip, then you get the same thing.
Yeah.
Is it crucial to require this to be a abelian loop?
A billion. Oh, so for loop, only Z2 can work. There's no Ennian loop here. Yeah.
Yeah, because I was imagining the following. You may have a loop that become itself after you flip, but
Yes.
it may have a non-abelian fusion rule. Is there such a loop?
Yeah. I think Liu He has some paper about a non-invertible fermion loop. Yeah, Liu He, are you here? Can you comment?
Yeah, well, like one can construct such a thing. I'm currently working with a student. Yeah.
Yeah.
Oh, I see. So you can potentially make this approach work for those non-abelian Z2 loops.
Yeah,
Yes.
exactly.
Okay.
Well, the thing is that
Okay,
well,
great.
for this kind of the invariance, as Eugen pointed out earlier, like there's no problem about the defining on the non-abelian loops or non-abelian particles. One can still like claim the invariance under perturbations. But well, so here in this current work that Ivan is talking, we are assuming the unitarity of the operators just to establish a quantization of the invariance. But yeah, up to that, one could still work on the non-invertible groups. Yeah.
I see. Thank you.
Yeah.
Okay.
Sorry, can I
Yes.
ask some question? I'm a
Yes.
bit confused. For Z2 loops, what does the arrow here refer to? What's the meaning of the
The
orientation?
arrow has no meaning at all. It's just like the blue and red color of my particle. So previously I labeled this particle by red and blue. It has no physical meaning. It just help you indicate like you can keep track of the identical particle. And here
Oh,
the
so
arrow
they can
here,
be this.
yeah, has no meaning. Yeah.
Oh, okay. Thanks.
Okay, now let me try to show to control this complicated process. Yeah. Okay, so first let me introduce this configuration space. So first, for each vertex correspond to a certain configuration. So for example, if the loop go to 0, 2, 4, 3, 0, so this is the loop in my conversion space somewhere here, yeah, like this one. So once we have this loop, you can notice we only need to use this black line to represent this loop, because once this black line has some endpoint, we just connect this endpoint to 0. So we can project this configuration into this symbol here. So we need to just label 1, 2, 3, 4, and a black line around them. So each label here corresponds to a closed loop configuration. For example, this corresponds to the vertex here. So each vertex is a closed loop. And now for each edges, it is the membrane operator. For example, on this loop excitation, if I apply the membrane around 0, 3, 4, so which means I try to apply the membrane operator here, so the resulting conversion will become 0, 4, 2. Yeah, so 0, 4, 2 will become this state. So we can try to connect all possible loop configuration, and you can see this becomes RP2 space. Why is RP2? Because you can see on the opposite vertex, they are the same, like here and here, here and here, here and here. So the configuration space of the closed loop, they naturally form the RP2. Yeah, so this is the meaning of this diagram. And now, what does this face means? So I will say face with the same color, they form the locality identity. For example, this yellow one. So, yeah. So consider these 2 yellow plaquets. I start with this state. So this state is nothing but the loop on the on the boundary of 0, 2, 3. If you can check this 2, 3 edge is this this one. So I go with 0, 1, 3, 0, 1, 2, 0, 1, 3 minus, 0, 1, 2 minus. So this is the plaquet 10 around this yellow face. And similarly, this one is this. So it is the edges involving 2, 4, and 3, 4. So 2, 4, and 3, 4 is these two edges. So this is my starting point. And I can apply the same thing, 0, 1, 3, 0, 1, 2, 0, 1, 3 minus, 0, 1, 2 minus. Yeah. So when we try to sum in over the edges of this 4 plaquet, this gives you the triple commutator. And more importantly, these 3 different phases, they have no overlap. Because once you compute the first commutator here, they have overlap on 0, 1 edges. But the 0, 1 edges and the 2, 3, 4 phase, they are spatially far away. So they don't have any overlap. So this commutator must be identity. So which means that this phase must be 0. So on this convergence space, I show you these 2 yellow plaquets. When you sum over them into the right orientation, this gives you 0. And same thing for all other phase with the color. So we simply sum in over all locality identity. So this is literally just the boundary of all phase in the RP2. So we know in the orientable manifold, if we sum in over all phase, you will get a 0 because the boundary of boundary becomes 0. But however, in non-orientable manifold, when you try to sum in over all phase, this gives you twice the first homology going across this RP2. So in other words, when we try to sum in all locality identity, this gives you some unitary process which square to 1. So for example, if we keep track of the orientation, this non-trivial homology is exactly this black thick line here. So we just need to follow this black thick line here. This is just the 24-step process, and they square to identity. So which means this gives you the Z2 invariant. And of course, this is not unique because, let me use a laser pointer. Because for this yellow plaquette, if I choose a different orientation, these edges disappear, will become these 3 edges, and these 2 edges disappear, will become these 2 edges. So we have many degree of freedom we can change. They are all equivalent because they are just differ by some identity. But however, if you choose this step, this will have 2 extra steps because this is 1, this is 3. So you will obtain some 26-step unitary. So that's the reason why in Vygotsky, Ha, and Hastings paper, they choose different convention. They obtain a 36-step process. So their process is longer. Yeah. So this is how we define this 24-step process and how we derive it. So we write down its conversion space and we try to study what's the all possible identity we can have. We just summing over all identity. Any question here? Yeah, this is a little bit technical.
A priori, why should we consider RP2?
Oh, because if you try to write down all loop conversion and try to connect the loop conversion by some membrane operator, they naturally form RP2. It's not I design RP2, it's I follow this rule. Yeah. I just follow these 2 rules and somehow they magically give you RP2. And the physical meaning of this RP2 is very clear. If you go to one vertex here to the opposite one, the orientation of the loop, they flip. Yeah.
Is there any field theoretic explanation of why RP2 is important here?
I don't know actually. Because from field theory, we will require a Klein bottle. That's why the CO junction free call it a Klein bottle invariant. But somehow the conversion space, the closed loop conversion, they form RP2. I don't see the connection. Yeah.
Thanks.
Hey, Yuan, can I ask a question based on what you have? This is the configuration space is RP2, assuming the ambient space is 3-dimension, or is it independent of that?
That's a good point. So I choose a particular tetrahedra with a center point. So this is you can think of it as my Hilbert space. But you can embed this Hilbert space into arbitrary higher dimension. Yeah. So although I derive this process in 3D, but it will work in higher dimension.
Well, but you could also say the same thing for the particle exchange, but you know that you cannot get anyon statistics in higher dimension.
Yeah, so that's a good point. So the T junction still work in higher dimension, but the quantization will change. In higher dimension, this will give you more locality identity, and this identity will constrain the T junction square to 1 instead of the 4 times to 1. Yeah. So here, yeah, you are right. So I missed a point. I haven't showed that in higher dimension, this don't give you more constraint. Yeah.
I see. So basically, maybe up to a certain dimension, the structure stabilizes in some way, and then
for particle, it stabilizes at 3 dimension. For loop, it stabilizes at 5 dimension. For membrane, it stabilizes at 7 dimension.
Oh, okay. I see. Thank you.
So there's an embedding theorem. For any p-dimensional cell, you can embed this p-dimensional cell into 2p plus 1 Euclidean manifold. Yeah. So you can see once I reach this 2p plus 1 dimension, I should capture already all structure. If you go to higher, this gives you no structure at all. Yeah. Okay, so due to the time limit, let me just briefly go through the overall logic. So from this example, it's already very clear. So how do we obtain the statistics? We just need to study all locality identity. Yeah, and we hope when we try to summing over this locality identity, let's give you some non-trivial number times something. Let me give you a particular example. So let me skip all this detail. So assuming I have this locality identity. So in principle, on lattice, I will obtain maybe 10,000 identity, but I can let the computer to solve it. So I have this constraint on this theta. Those theta, they are not independent. So first, I need to organize this theta into some matrix here. And then we compute the Smith normal form of this matrix. So what the Smith normal form does? So first we do some rule operation to cancel to minimize the number of the non-zero row, and then we redefine the column. But for example, I redefine the theta 1 prime, theta 2 prime into this linear combination. I can make this equation into the fully diagonal one. Once we reach this one, it's easy to interpret the meaning here. So this says 1 times theta 1 prime is 0. So which means theta 1 prime is kind of meaningless. It's trivial. And similarly for this theta 3, the theta 3 has no function at all. The only non-trivial thing is here. 3 times theta 2 prime equals to 0. So which means this theta 2 prime give you some Z3 invariant. And the way is summing over all original theta give you the process. So this is exactly what we do in our RP2 case. We just try to find some certain combination of the locality identity. This will give you twice times something. So this give you some Z2 invariant. So in principle, if we can make the summation into n times something, this will give you some Zn statistics. So our setting is very general. Let me go back to maybe here. Yeah. So we need to specify all possible configuration type. So for example, there can be membrane, there can be loop, there can be particle. So this is my Hilbert space. And then we define some operator which move my excitation, like the hopping operator on the string or hopping operator on the membrane. It will move my excitation. The only thing I need to do is I need to study the locality constraint for this hopping operator. It's like if those operators they don't have the common overlap, their higher commutator must vanish. So we just need to impose a lot of this kind of condition into my computer, and I use the linear algebra Smith normal form to compute what's the final answer for this Zn statistics. Yeah. So this is the logic of my approach. So in the last few minutes, let me just show you some interesting results. Yeah, so I actually only go through the half of my slide. Sorry for my bad time management, but there are some key observations. So
Sorry,
first,
can I ask some question first? By the
yes.
way, there's no time limit. Don't worry.
Oh, okay.
Also, so when you said you want to find all the locality constraints, can you explain
Yes.
again how do you make sure that you find all of them? You said
Let
for
me.
very large lattice there can be many.
Yes. So in principle, we will choose the n sphere, the triangulation. Let me n simplex. So we will choose the n simplex, and the dimension of the is finite, but it can be large, like the 2 to the 10, for example. If like this one, so this we have 10 edges. So for the loop configuration, it should be the 2 to the 10. This is my Hilbert space. And for operator, it can live on any membranes. It also has 10 membranes. Yeah, so we have many choice. So we need to consider all of them. So actually for this one, we only need to consider triple commutator, I believe. Yeah, so you just try to list all triple commutator and try to, so each one give you one very long row, a row of maybe 1,000 entries. And finally, you will obtain like a 1,000 times 10,000 matrix. So this is why we compute a Smith normal form.
But all these locality constraints come from a single simplex.
Yes. So here we restrict ourselves into a single simplex, and we believe, we don't prove it, but we believe if you make this simplex more complicated, for example, you have extra vertex or extra face something, we hope the answer will not change.
Thank you.
Just like the T-junction. T-junction is a triangle with a single vertex. But if you consider two triangle or three triangle, this will not give you extra index because we only have the topological spin. So we cannot have more index.
Thank you.
Okay, so based on our numerical computation, we try the particle in 1D, 2D, 3D, loop in 2D, 3D, and or membrane in 3D. We can obtain some index. And magically, the index will match this cohomology group. Yeah, so in some sense, this is what we expect from the field theory, because when we say excitation has anomaly or not, is corresponding to whether we can gauge the wall line of this particle. If this particle is boson, we can gauge it, we can condense it. If it's fermion, we cannot condense it. So this corresponds to SPT in one higher dimension. So this is exactly the data I write down here. Yeah, for those who are not familiar with this Google module, it doesn't matter. It just means it corresponds to the SPT. For example, my particle in 2D, my particle in 1D will correspond to SPT in 2D. Yeah, so that's why we have this S3 index here. So you can think of this anomalous particle live on the boundary of this 11 group SPT. Okay, so here I am going to show you some results. So this is the Caroline's formula I already showed you. And this is the 24-step process I derived. Also agree with the Vygotsky, Hart, and Hastings. And I propose something new. So we can consider the F symbol for loop and the F symbol for membranes. So I hope, because there are some recent papers by Sahan and Wilbur, they also try to make this F symbol in 2D loop more rigorously. I haven't tried yet, but I believe once I find a correct way to simplify their formula, they should match my quantity here. Yeah. And more exotically, so we can apply our methods to mutual statistics. So we can consider both particle, loop, and membrane excitation at the same time. The simplest one is the mutual braiding. For example, the particle goes through this phase, can have some plus minus sign, for example. So this is a very typical statistics in like a 3D torical. It's nothing but a commutator. So first I move the particle here, then I create this loop excitation, and I move my particle back. I shrink my loop excitation. So this commutator will teach us the braiding between this particle and loop. So this is well known, and my computer does provide this index. However, I try to implement our algorithm into loop membrane, particle membrane. They give us some extra statistics. So for example, I have some loop excitation created by some membrane operator. And I have some membrane excitation created by this volume operator by tetrahedra T. And we can compute this quantity. So it looks like we have some T-junction process for this F1, F2, and F3, and commutator with this UT. Yeah. It turns out that this index is useful to distinguish the beyond cohomology phase. So there's an additional paper by Vygotsky. They have this 4 plus 1D Z2 SPT. Z2 beyond cohomology SPT is this one, AW2 squared. Yeah. So we find that this index is important to characterize the boundary of this anomalous SPT, the beyond cohomology SPT. Yeah. So this is still something we expect. But for these two, for particle membrane statistics and this loop membrane statistics, what do they do? I don't really know. So this result is just some some Smith normal form algorithm give us, but we don't have a very good geometrical interpretation. What does this actually means? Yeah, this is still open question. Okay, so
Sorry,
maybe
when you say what it means, you mean what it means in higher dimensions or what?
no, I mean for this one, it's very clear a particle goes through a loop and this become a mutual braiding, right? But for other process, how do I see it correspond to certain geometrical process? I don't
Oh, I
know.
see.
Yeah.
I see.
But they are correct. This is a guarantee. So we have some numerical way to check this is invariant, but I just don't have good understanding about them. Okay, so maybe a little bit late, but this is the main point of my paper. So we want to say anomaly of the symmetry equal to the statistics of the excitation in the symmetric subspace. What does this mean? Let's consider the simplest 1 plus 1D anomalous symmetry. It's a product of X on all vertex times the product of control Z on all nearby vertex. So this is the boundary of Leavengood SPT. Or more precisely, this is the boundary of the CZX model in Chen's paper. And the CZX model is exactly the same phase as the Leavengood SPT in 2D. So this is anomalous 1 plus 1D symmetry. So given the symmetry, first we need to obtain the symmetry operator. So we need to write down some operator which commute with this symmetry. If you believe in me, there are two generators. The first one is ZZ term. Of course, because this ZZ will commute with the product of X on all vertex. The second one is X times control Z of the nearby vertex. So due by some careful computation, you can check this hopping turn commute with this symmetry. Yeah. So you can think of this W turn as some domain wall. This domain wall will tell you whether the two nearby vertex they have the same spin or not. And this U operator is the hopping turn of the domain wall. And to check this is anomalous symmetry, we just need to compute the fusion statistics of this hopping operator. So it's nothing but the 0, 1 square times and the commutator with the U1, 2. So we apply the same formula here. We compute this square with the commutator with its neighborhood. Let's give you a -1. Yeah. So this is our interpretation. So typically when we try to argue this is the anomalous symmetry, we need to follow like the Elsnaya procedure. We need to do truncation, do dimensional reduction, and finally it will give us some Spherical cycle. And our approach is simpler. We actually maybe not simpler, but just alternative approach. The most difficult part is finding this hopping operator. Yeah, how do we find a generator of the commutant algebra? It's also difficult, but in this case, it's very elegant. Any question here? Yeah. Okay, so maybe this example is simpler. Maybe I should use this one first. Yeah. Consider the 2 plus 1D with some anomalous one-form symmetry. In generated by this symmetry operator at each vertex. It's product of X times product of Z. And the commutant algebra is very easy. The first one is just a flux turn here. And the second one is the hopping turn. But the hopping turn is X times Z. And you can check this hopping turn commute with this gauge constraint. This is exactly my 2D Bostonization, the first paper I wrote with Anton back to 2017. Yeah. And you can, it's easy to see here because if you have the torical picture, this is the hopping of the fermion in the torical. So if you try to plug in this hopping operator into the T-junction process, this will give you the -1. Yeah. So that's why we say this 2D one-form symmetry is anomalous. Okay, let me give you the slightly non-trivial example. This is the example I wrote in our paper. So consider there's a Z2 times Z2 symmetry. So at each vertex, we have two types of poly, ZA and ZB, and similar XA and XB. So one Z2 is very simple, it's a product of XB, and the other Z2 is slightly non-trivial, it's a product of XA on all vertex times some control Z on O plus K. So this control Z is like a 1, 2, 4, and 1, 3, 4. In terms of this B equal to 0 and 1, it is nothing but B1 times B2 times B4 and B1 times B3 times B4. So this is the Z2 symmetry of this type A. So this is anomalous. Why? We can first we need to define the symmetry operator. Like the domain wall, it's just like the Isington like before. And for Harpington, it's slightly complicated. But if you believe in me, it's just some poly X at 5 times some complicated phase vector. It's the control Z on the sixth triangle nearby this vertex 5. For example, 5, 1, 2 is this triangle, 5, 2, 6 is this triangle. So this is the control Z between A, B, B. Yeah. So if you trust me, this term commune with this symmetry. And finally, we just need to plug in this Harping operator into my loop fusion statistics. So I need to divide my region into ABC like this one. Once you plug in into this one, you can check it's -1. Yeah. So that's how we argue this is an anomalous Z2 symmetry. Of course, you can follow Elsnayak's procedure. Also in Anton's recent paper, he has the coarse module homotopy method. I forget the name, but in his paper, he checked this example. So follow his algorithm. He also compute something and get a -1. Yeah, but it's different from our computation. So from my point of view, once the commutant algebra like this U is found, it's much more straightforward for us to just plug it into our statistic to check it's +1 or -1. Okay, so due to the time limit, maybe I should skip. We have some additional result for membrane excitation, but things go much more crazy. I don't want to go into detail. So maybe it's a good time to end here. So let me just give you a quick summarize. So first, we define a very universal microscopic definition of statistics on lattice. So we provide an algorithm. We start from some locality identity of this unitary operator, and we just input all possible locality identity into the computer and compute the Smith normal form. And this Smith normal form will give us the right index, including the Zn statistics and its process directly. And this will work for arbitrary dimension and arbitrary excitation. And I don't have time to list, but I try to claim our non-trivial statistics can define the anomaly of symmetry, and also it will constrain some low energy behavior, like the Benny Yoshida's paper. He said if we have fermion, the underlying ground state must be long range entangled. Yeah, so the same conclusion holds. Yeah. And for future direction, like the Liu Jun point out, we can actually work for non-abelian anyon or even non-invertible symmetry. As long as the U is finite depth circuit, our argument should work. Yeah, but the physical interpretation will become less clear. Like Liu Jun's point, if we don't have a very well-defined Hamiltonian, how do we make sense of anyon or excitation? That's a very important physical question. And also, for our paper, we just provide a lot of observation, like the latest definition somehow match the group cohomology of higher group. But however, until today, we don't have a very rigorous proof why this is true. Yeah, it's related to the simplicial complex, and we need to establish a very rigorous connection while our statistics will match the structure of like Ellenberg-McLean space. I have no idea how to do it at this point. And also, as I mentioned before, our algorithm just output some index, some quantity, but we don't have a very good understanding. So in some case, we do have. So for example, the particle exchange, loop flipping, or the mutual braiding of the particle and loop. So the process is very clean, and we can see what's going on. But for higher dimension or mutual statistics, for example, I can show you this membrane excitation. We have this 56 step. I can apply this on some initial state, and this will output some plus minus one index. However, I don't have any idea what's going on here. So actually, it's not plus minus one. It's the Z3 index. So this will give you some Z3 index on this red part. But if you just try to study the automorphism of the sphere, the two sphere, go to two sphere, maybe the diffeomorphism, there's no Z3 component. So there must be something extra going on. We need to consider the framing on the two sphere. And the framing on the two sphere, if we consider some homotopy classification, it will have some Z12 classification. So this Z12 contains a Z3. But at this point we cannot say much. So we just output some concrete process, but we don't have a good geometrical understanding. Yeah, so that's all my talk today. Yeah, sorry I skipped many details, but if you are interested, we can always talk in person, and I'm happy to describe them. Yeah, thank you.
Yeah, thank you, Yuan, for the very interesting talk. Other questions? I have a question. So here in this talk, you focus on the generalized self-statistics, right?
Mm.
So
Right,
for
including some mutual one, like there are some mutual statistics.
mhm. Do we know the this is related to the general question of whether we know this set of invariants are the complete set of invariants. For example, here do we know that self-statistics completely determines all the mutual statistics?
No, they are independent. Because let me give you a counter example, like the loop here, So, like the loop in 3D, if you consider Zn times Zn loop, the self statistics, like a Z3 times Z3 loop, for example, like a Z3 loop has no self statistics, but they have mutual statistics.
Okay. Mhm.
Yeah, so the anion in 2D is special because the braiding is determined by spin, but this is not true in higher dimension. Yeah.
Mhm. But here, maybe I missed this. Do you think you get a complete set of invariants for mutual statistics?
I see, at least for the field theoretical perspective, I think we can reproduce all possible invariant. But there are some recent paper by Wenjie, Dominic Els, Wilbur, and Michael Levin, Curlin. So they have extra lattice index related to the translation. So they study some symmetry. If you do apply it twice, this will equal to translation around the boundary. So this is additional QCA index they propose, like H3 from G to QCA or something. This is not captured in my paper. Yeah. So on the
Yeah, but
lattice, they are
that
extra.
that's their unsetability index. That index is the obstruction to making the symmetry on-set, right? It's not necessarily any obstruction to making the states short-term entangled.
Right. So we are talking about Tohu Vanami. So it's like we cannot find a symmetric short-range entangled state.
Yeah.
So once we have a non-trivial statistics, this is the abstraction to find a symmetric eigenstate as a product state.
Yeah.
So in some sense, we are more robust. Like it's more problematic abstraction to gauging actually.
Yeah, I do think this is more important because who cares whether the symmetry is on-site or not?
But
If the
Liu He and
symmetry,
we wrote another paper about on-siteness. It's also interesting.
of course, it's interesting, but I think it's less important as whether it's an obstruction to symmetric short-range entangled states.
Yeah, I agree. Yeah.
Yeah, okay. Any other questions? Okay, if not, I will represent everyone to thank Yuan again for the very interesting talk. Thank you.
Yeah. Thank you. Bye bye.
Yeah, bye.